Hi, today we'll be discussing about Instagram system design. If you are asked to design system similar to Instagram, then there could be multiple requirements. Like let's say a user can post story which can last for 24 hours, or those stories can be saved in highlights or close friend options, direct messaging, and so on. There could be endless multiple requirements. But for the scope of our video, we'll be considering some functional as well as some non-functional requirements. So starting with functional requirement, a user should upload media, either image or video. So basically a user can post on his or her profile. A user can get feed. So when we open Instagram, we see feed where we have a post of different users which we follow, and a user can like and comment on those posts as well, and a user can follow another user as well. So these are the functional requirements. Going forward to non-functional requirements, the system should handle 1 billion registered users. Its availability should be high, and it could handle geographically distributed users, because of course if there are 1 billion registered users, then the users would be from multiple geographic locations as well. So these are the functional and non-functional requirements we should consider. Okay, so let me show you some calculations as well, because for handling 1 billion registered users, what amount of bandwidth should be required, what amount of storage should be required, or what transactions per second should be required. So okay, let me show you some calculations based on that. So yeah, we have 1 billion registered users, right? And out of those 1 billion registered users, we can assume that the active users are 25%. So 25% active users we have, which makes around 250 million users. So 250 million users are daily active users. Now out of this, let's say they access Instagram for 10 times per day on an average. So a single user access 10 times per day, so 2500 million of requests per day are being sent. So let's say, right, these are the requests for read. Okay, let me write it down that as well. So these are for reads. So 2500 million requests per day are being sent. So if we convert that to seconds, 2500 million divided by 24 hours into 3600 seconds. And for the ease of our computation, what we can do is we can consider this value as let's say instead of 3600, we would consider it at 2000, and instead of 24 we'll be considering it as 25. So which will give us 2500 million divided by 50,000. So 2500 million divided by 50,000, which gives us somewhere around 50,000 transactions per second. So these 50,000 transactions per second are reads per second. Let me write it down as well. Reads per second is 50,000 TBS. Now let's calculate its bandwidth. So for bandwidth, what we require is this transactions per second. So 50,000 transactions per second, and let's assume we have 200 kb of an average media size. So let's say if we are considering an image or a video, there could be more than 200 kb or less than 200 kb, but on an average we are considering it as 200 kb. So which gives us somewhere around which gives us somewhere around 10, okay, 10 GB PS. So 50,000 into 200 kb is 10 gbps. Okay, so it gives somewhere around 10 gbps of bandwidth. So this is the bandwidth required for reads. Now going forward for writes, now all the daily active users will not post daily. So let's consider 20% of daily active users post uh, one item. 20% active users post one item daily. So their requests would be somewhere around 50 million requests per day. So this would be for writes, 50 million requests per day. If we convert it to, let's say, convert it to seconds, considering 50k here as well, as we consider it in reads, so we'll be getting it around 1000 transactions per second. So 1000 transactions per second is our writes per second. Let me write it down here. Writes per second equal to 1000 transactions per second. Now if we calculate its bandwidth, then we get 1000 into 200 kbps. So 1000 into 200 kbps gives us somewhere around sorry, not kbps, kb, because it's the image size, and this is tps here as well, 50,000 tps. Okay, so this gives us around 200 mbps, right? So 200 mbps for writes would be the bandwidth required. And if we consider storage, then let's say this 50 million users are posting records around 200 kb per day. This is per day, which comes around 10 terabyte data per day. And this 10 terabyte, if we convert it to this is per day, so for an year how much storage would we require is 365 into 10 terabyte per year, so which would be 3.65 petabyte per year. So 3.65 petabyte per year storage would be required. So these are the assumptions which we need to make before designing a system like this. So these are those calculations. So moving forward towards data modeling, let's look at the data modeling as well. Starting with user, we'll be having user ID. So each data modeling object would be having its primary key, its ID. So user has a user ID, username, email, contact, password, creation time, and modification time. This is for user. Going next towards media. So media has media ID, its primary key, user ID, its foreign key. Which user is posting the content, it's for that user ID. Media type, what is the type of media, image or video. Then a media URL or blob ID. So the image or video we won't be directly storing in the database, but what we'll be doing is we'll be storing it in some blob storage or Amazon S3. So the location where that particular file is stored is either the location URL or a unique ID is stored here in media URL or blob ID. Now we will also store caption of that particular post, the location, that is in terms of latitude and longitude, the creation time and the modification time. Going forward to like object, ID, its primary key, media ID, which post is being liked and which user is liking that post, so user ID, and its creation time. Similarly for comment, comment ID, media ID, which post does comment belong to, user ID, which user has commented, comment text, what is the comment and is edited, boolean, like we have an edit option in comments as well, so is it edited, and at what time it was created and what time was it modified. Then comes follow. So we have here details of followee, follower, and creation time. So followee is a person who is being followed, and follower is a person who is following. Going forward to account info. So account info store information like followers count or following count, last login, and so on. Last login for managing sessions of the login and so on, and followers count and following count uh, to avoid querying every time from this database the follower mapping, because if we have 1 billion users, and imagine if even one user follows 1000 other people, so this would be there could be multiple entries in this table, and the query would be heavy. So for count, so will be storing the values when a user is following some another user, then the followers count and following count would be updated and would be fetching this records when a profile of that particular user is being viewed. So that is account info. And next comes feed. So feed would be containing feed ID and list of media ID. So what media are being displayed in a person's feed is stored here as a list or an array. So yeah, that's it about data modeling. Now going forward towards our high level design. So for high level design, let's say it starts from client. A client calls an API for the functions, let's say media upload, feed, like and comment, follow. Each of these functions would be like each of these 4 functions, which are our requirements, would be having different services. It is possible that they may have same service, but here we have different services. As Instagram follows microservices architecture, what happens here is we don't directly configure each and every microservices to client, because let's say if a new service is being added, or we need to remove or replace an existing service, then it becomes difficult to configure each and every time in the client, and the client part of code is also being modified in that scenarios. So API gateway is being used here. What API gateway does is, those who don't know, it redirects the APIs to their respective services. API gateway also manages rate limiting, or load balancing, or event logging, and so on. It even monitors. Here I have shown load balancer. So what load balancer, even load balancing is being managed by API gateway. So what load balancer here will do is, it will manage the loads of multiple servers. Obviously we would be requiring multiple servers, because there would be high traffic on services like, let's say, like and comment. So like and comment service may have high traffic, follow service may not have that much high traffic. So there means low number of servers for follow may do, but high number of servers for like and comment would be required. So the API is redirected to which server is being decided by load balancer. Now let's check this one by one. When media upload API is being called when a user posts something. So when a user posts something, media service, the API goes to this media service, and what media service does is it stores the image or video in this blob storage, either blob storage or S3. So it will store the image here. It will also generate a unique ID, or let's say a path of this S3 location, and will store that path or unique ID of that particular image along with its other information like caption of the post, or which user has posted, so user ID and so on. So all those information will then be stored in the database through this metadata service. So through this metadata service, that particular information would be stored in database. Now when I talk about database, we would consider both relational and NoSQL database, because both are being used in Instagram. Relational database is used because let's say user mapping or means structured data like user mapping or followers mapping or like and comment mapping and so on, the mapping of posts and so on. So all this structured data is being stored in relational database where data consistency is to be maintained. And data such as, let's say, for analytics or for recommendations, whatever data is required, those data are stored in NoSQL database because those data are in a large amount, and those are to be processed through distributed systems. Distributed systems, those need to be processed, so that requires NoSQL database. So Cassandra as a NoSQL database here is used. Going back to our media service, so after the information of that particular media is stored in database through metadata service, media service would call broadcast service. So what broadcast service will do is, let me explain you with an example. If I am posting something, when I post an image, after my details getting stored in database, it will call this broadcast service. The broadcast service will fetch all my followers and this media service information as well. Now this media service information would be fetched through CDN. Now why not directly through database? So it not necessarily every time will go to blob storage. It will call means it will get the content from CDN. Now CDN is content delivery network, which is a network of multiple servers across the globe to get the to reduce the latency and to reduce the cost of this S3 query calls. And it will store the images in cache. So this CDN is used to fetch the image. And let's say media service is concerned, then media service will then call the broadcast service, where all my followers would be called, and those records would be passed further to message queue, and those information from message queue would generate a feed through feed generator, and feed generator would then populate those generated data in cache. Now when a user opens Instagram, this feed API is being called, and feed API through feed service will get the feed data from cache, which was generated by feed generator. Now if a user wants some new feed, then he or she refresh the screen, then the feed service again call feed generator, and the information from message queue will again get into cache. Now when a user like and comment a post and calls a like and comment API, then like and comment service is being called, which then updates the data in database through this metadata service. And same thing happens with follow. When a user follow another user, a follow service is being called and metadata is being updated. So yeah, that's all about Instagram system design.